Okay, so for 51D, we're trying to figure out the kilojoules of heat needed to raise the temperature of an amount of water. So when we're solving for a heat, we are going to use the equation heat equals C times mass times delta T. So because we're talking about liquid water, we know that our C is 4.183 joules per gram degrees Celsius. In the question, we're given that the mass is 10.00 kilograms. We're going to need that to be in grams because the specific heat value is over grams. So we need to convert that to grams. Which gives us 10,000 grams. And then our delta T, we take our T high minus T low, so 46.2 minus 24.6. Which gives us 21.6 degrees Celsius. So now we're ready to plug all of that into our equation. And we take 4.183 times 10,000 times 21.6. Now that 10,000, it was in 4 sig figs, so really I should be plugging this in as 1.00 times 10 to the 4th, just in order to keep our significant digits. So it doesn't change the actual numerical value, it's just changing our sig figs. So this is going to give us 903,528 joules. That's a really big number. And so what we're going to do is actually put that into kilojoules, because scientists, we don't like big numbers. And we also want to have a maximum of 3 significant digits because of that 21.6. So that 903 becomes 904, and then we're dividing by 1,000 to get to kilojoules, so it becomes 904 kilojoules. Okay, so that's the answer to 51A. Next, you had to do 53A, so let's look at that one. Okay. So for 53A, we're solving for the joules of heat again needed. So this is going to be that same equation where we have heat equals C times mass times delta T. Okay. So for this problem, we are told that the mass is 80 grams. And that the temperature is being raised from 10 to 25. So we take high minus low, right? 25.0 minus 10.0, okay, gives us 15.0 for our temperature change. And then C, this is something we have to look up because you're not required to know the specific heat for octane. And so they tell us that it's 2.22 joules per gram Kelvin. Okay, but remember it's the same thing as degrees Celsius for these types of problems. So now we're ready to plug this in, and we take our 2.22 times the 80 grams times our delta T, which was 15.0. We check our significant digits. We plug this in. We want 3 sig figs, and we're going to get, let's see, 2.66 times 10 to the 3rd joules. That answer's fine, or you can just mark it as 2.66 kilojoules. Either one of those answers is fine. Then you had to get into a bunch of Hess's law problems. So we'll take a look at those next. You had 3 Hess's law problems to do. Okay, so for 63, you're given your target, and then you have two step reactions to work with there that we need to manipulate to make them work. So our target is P4O6. I'm going to leave out the states of matter for right now, just because I'm trying to get through your homework so you can move on. So we've got that. Nope, that's not the target. That's our half reaction. Our target was the P4O6 plus the 2O2 gives us P4O10. So that's our target, and we need the delta H for that. We've got the step reactions. P4 plus 3O2 gives us P4O6, which has a delta H of negative 1,604.1 kilojoules. And then our other step reaction has P4 plus 5O2, giving us P4O10 with a delta H equivalent to negative 2940.1. Okay, so we're trying to make our step reactions match. We notice we have P4O10 up here on the right, and in our step reaction we have P4O10 on the right, so this reaction is going to be good to go. Here, however, our desired reaction has P4O6 on the left, whereas here it's on the right, so we're going to need to flip this reaction. Remember that when we flip a reaction, we got to flip that sign, okay? And so we're going to now end up with P4O6 yielding P4 plus 3 oxygens, and now that delta H is going to be positive 1,604.1. And so we check, and we've got P4 and P4, so those are going to cancel out. We have 3O2 and 5O2, so the 3O2s go away, and this is going to change to 2. And so when we add up our step reactions, we end up with P4O6 plus 2O2 gives us P4O10. And then our delta H now is going to be negative 1,300.0 kilojoules. Okay, so that's the answer to 63. Next, you had to do 65. Okay, so there are our target reactions, C2H4. Okay, now we've got 3 step reactions. Okay, so again, trying to hit that target reaction here. And so we check. We've got C2H4 here on the left, and this bottom reaction, it's on the right. So I know I'm going to need to flip that one. So now I've got, that's going to change this reaction. And now we're going to have C2H4 giving us the 2 hydrogens and the 2 carbons. When we did that, that also changes the sign of our delta H. And so now that's going to be a negative 552.3. There is a decimal there. It's hard to see, but it's there. Then we look at our other reactions. Let's see here. We need CF4 on the right. CF4 is on the right here, so that's okay. We need HF to be on the right. HF is on the right here, so that's okay. But if we look at our coefficients, I need 2 CF4s and I need 4 HFs, which means I need to multiply both of these equations by 2, which is going to change these coefficients to 2, 4, and 2, which then I need to multiply my delta H by 2. And then this reaction I'm also going to need to multiply by 2 to match up those HFs. So I end up with 2H2, 2F2, and 4HF. Okay, so we put this all together and we end up with what we wanted, C2H4 plus 6 F2s, right? We've got 2 here and 4 here, which gives us 6 F2. Headed to our 2 CF4s and the 4 HF. We add that all up, we add up our delta H, and we'll end up with negative 2.49 times 10 to the third kilojoules. Okay, so that's the answer to 65. Okay, then you had one more problem, which was an even numbered problem, so the answer to that one was not in the back of the book. So let's go ahead and go over that one. Okay, so 66 was the last one. Let's see our target, N2O. This one has three-step reactions. Okay, so trying to match everything up here. Let's see, we've got NOs in lots of places, so I'm going to choose not to start there because there are so many of those. Instead, I'm going to focus on the N2O and the NO2. Down here, I have the N2O, and that's the only place where that appears, and I only want 1, and I have 2. So I need to multiply this whole reaction by 1/2. And so by doing that, right, I'm going to need to multiply my delta H by 1/2. And then that's going to change all my coefficients. So I end up with 1, 1, and 1/2, actually. And that's okay. It is okay to have fraction coefficients when you're doing Hess's law. All right. Then we look at the equation above. That's where we have the NO2. And look, the NO2 here is on the right, but we want it on the left. So I need to flip this reaction. Also note that I have 1 here and I have 2 here. So I'm going to need to multiply that equation by 1/2 also. So I need to flip it and multiply by 1/2. And if I do that, I need to do it to the delta H. I need to flip and multiply by 1/2. And so this reaction is now going to become NO2 gives me NO plus 1/2 O2. And then this reaction above, if we look, the N2s cancel. 1/2 O2 and 1/2 O2, that's going to cancel with the O2. These NOs are going to combine, which gives me my 3. So I've got my target. I've got N2O plus NO2 gives me 3NO, and I plug that in, and I'm going to get a delta H of 155.7 kilojoules. Okay? Don't forget to apply the changes